Okay, so in the previous video, we spent time developing the idea of a permutation and came up with a formula for it, used it in a couple of different examples. And remember, the point of a permutation is in cases where we are given a set of n objects and we want to choose from that r objects. So we're choosing a certain number of objects from a potentially larger set. And in the case of a permutation specifically, the order of selection matters. So we consider a first selection followed by a second selection, and we pay attention to the order when we're counting those possibilities. Combinations, which we're going to talk about next, are similar in the sense that we're choosing a finite number of objects from a potentially larger set. But in this case, we don't consider the order to matter. And we considered a case where we're selecting 3 letters from a 5-element set, and we listed 6 of them in a previous example where it's the same 3 letters just with different rearrangements. And we discovered, in fact, I'll go back to that example, we discovered that if you already knew what the permutation was for that problem, then to find the combination, to think of all the different choices of 3 letters from a 5-element set where the order didn't matter, we had to divide by 6 because 6 was the number of ways of rearranging any of those 3-element selections. But where did the 6 come from? Well, it came from 3 factorial because that, as we showed in 10.2, is always going to be the number of arrangements of the number of rearrangements of a 3-element set. Okay, to generalize that a little bit, now instead of just selecting a 3-element set, we're selecting an r-element set. Okay, so again, if you're looking for a combination, the total number of ways of selecting r objects from a set of n in such a way that the order doesn't matter, we can first think about what would be the case if the order did matter. We would have a permutation. And then that permutation would contain a bunch of redundant selections. So we need to divide by r factorial because r factorial is going to represent the total number of rearrangements of any of those selections of r elements. This is mimicking what we did in that previous example. We came up with a formula for the permutation. It was n factorial over n minus r factorial. We're dividing that by r factorial. To simplify this rational expression, I can bring n minus r factorial down into the denominator and I get this. This is my formula for a combination, and we write it using this notation, NCR. Okay, now a couple of notes on this. First of all, notice this is very, very similar to the permutation formula. It just has this added factor of an r factorial in the denominator. Okay. Another thing to mention is when we talk about combination problems, the terminology we typically use is the word choose. So when I see NCR, the way that we read that is N choose R, meaning N objects and I'm choosing R of them. Now this notation, NCR, is I've found that it's fairly common in introductory level textbooks on this concept. But as you kind of move into other areas of math that use combinations like probability theory and stuff like that, we actually don't use this notation much outside of this. Instead, we use this notation. It looks like a fraction without the line, n over r, and it has these parentheses around it. This means the same thing as this. So if you encounter this notation, just know that these are the same. Okay. Here we want to, in this example, determine the total number of 5-card poker hands that can be dealt from a standard deck. Now, poker hands, if I'm dealing you 5 cards from a standard deck which contains 52 cards, the order in which I deal those cards to you doesn't matter. If you've ever played poker, you know that once you have a 5-card hand, the card that was dealt first, it doesn't matter that it was dealt to you first. The point is that you have those 5 cards and you can use them in the game. So this is a case where order doesn't matter, but we are making a selection process without replacement. You can't be given the ace of spades twice because there's only one ace of spades in the deck. So this is a combination problem. Again, 52 cards to choose from and we're selecting 5 of them. And so here's in a case where I would use that formula. 52 factorial over r factorial, which is in this case 5 factorial times 52 minus 5 factorial. Remember, don't evaluate 52 factorial explicitly. It's a gigantic, gigantic number. We use cancellation instead. This is equal to 52 factorial over 5 factorial times 47 factorial. Now, in order to simplify this, the most efficient way to do this is to find the larger of these two factorials down here and use that to cancel out a bunch of terms from this up here. Notice 52 times 51, I'm kind of writing out the beginning of 52 factorial. 52 times 51 times 50 times 49 times 48. And that's all I have to write, because after this would become 47 times 46 and all the way down to 1. All of that's going to cancel with this 47 factorial. I also have 5 times 4 times 3 times 2 times 1 down here, because that's what's left. Once I've canceled 47 factorial, I have 5 factorial left down here, and that's what's going to remain. Okay, from here it's still a big computation, and yeah, you could plug this directly into a calculator as is, but it's nice to look for things that cancel. So for example, 5 times 2 is 10, and 10 will cancel with this 50. That leaves me with a 5 right there. What else do I have? I have a 4 and a 3. Well, 4 times 3 is 12, and 12 goes into 48 4 times, so that's going to become a 4. And then this 1 down here doesn't really affect anything, so we can kind of ignore it. Really what I have now is 52 times 51 times 5 times 49 times 4. Probably still use a calculator at this point, but now it's minimized the amount of stuff you have to punch into your calculator. You get a large number from this. 52, choose 5. Once you've worked all of this out, it's going to come out to 2,598,960. That's the total number of 5-card poker hands. That's a lot, right? Notice there's a follow-up question. How many of these poker hands consist entirely of face cards? This requires you to know a little bit about poker, or about a standard deck of cards. So if you don't play cards, you don't really know what's in a deck of cards, it's important that you know that there's a total of 12 face cards. There's a jack, a queen, and a king. That's 3. And there's 1 for each of 4 different suits. Hearts, clubs, spades, diamonds. So that's 3 times 4, which is 12. That means I'm still choosing 5 cards, but I've narrowed down the set that I'm choosing from. Instead of choosing from 52 cards, I'm only choosing from 12 face cards. So the second problem is 12 choose 5. 12 factorial over 5 factorial times 12 minus 5 factorial. And again, we go through the same simplification process. 12 minus 5 is 7. Choose the larger factorial and use that to help cancel. 12 times 11 times 10 times 9 times 8. That's where I would stop after canceling. 5 times 4 times 3 times 2 times 1. And once again, look for things that cancel conveniently. 5 times 2 is 10. That cancels completely with that 10. 4 times 3 is 12. That cancels completely with that 12. What I'm left with is 11 times 9 times 8. And this is a considerably smaller number than what we just saw. This comes out to 792. Okay, so that's a couple of, well, it's really one example with 2 parts, but involving combinations. Let's look at some more. In this case, we've seen a problem like this before. I'm choosing a committee of 4 people, and I have a total of 10 candidates to choose from. But there's some criteria that this selection process has to meet. We're selecting 4 candidates, but we want equal representation between men and women on this committee. Now, of these 10 people, of these 10 candidates, 6 of them are men, and they both say men. So it actually should have been 4 of them are men, and 6 candidates are women. Okay? It says how many committees can be chosen consisting of the same number of men as women. Well, if it's a 4-candidate committee, that means that we want 2 men and 2 women on this committee. So from the 4 men, I want to choose 2 of them to be on this committee. Okay? What is 4 choose 2? Now, let me say men. 4 choose 2 is 4 factorial over 2 factorial times 4 minus 2 factorial, or 4 factorial over 2 factorial times 2 factorial. This is equal to 4 times 3 over 2 times 1. Notice I've canceled the 2 times 1 here with this 2 factorial here. Let's cancel that 2 with that 4, which leaves me with a 2. Gives me 6 possible choices. So there's 6 different ways to choose 2 men out of those 4. And again, for a committee, the selection or the order of selection wouldn't matter. It doesn't matter who was chosen first and who was chosen second, because they both end up on the same committee. What about for women? Well, again, we have 6 women to choose from this time, but we only want to choose 2 of them to go on this committee. So that becomes 6 factorial over 2 factorial times 6 minus 2 factorial, or 6 factorial over 2 factorial times 4 factorial. 4 factorial is the larger number. Use that to help cancel more factors from up here. 6 times 5 is my numerator. 2 times 1. Notice this is 30 divided by 2, which is 15. Okay? Now, that doesn't answer the question, because that just says how many different ways can we choose the men for this committee, how many different ways can we choose the women for this committee. We now can take these results and finish this off using the fundamental counting principle. Notice we're still using the fundamental counting principle in conjunction with these permutation and combination problems. So if there's 6 ways of choosing the men for this committee, and there's 15 ways of choosing the women for this committee, then 6 times 15, which is 90, would tell us the total number of possible committees that can be chosen meeting our criteria. Okay? One last example to wrap things up here. I like this example. This is a pretty classic problem. At a party with 2 people, every person at the party shakes hands with each of the other party goers. How many handshakes take place? Now, looking at a problem like this, it doesn't feel like a permutations or a combinations problem, but you can actually think of it in terms of a combinations problem. So if you number the people off, 1, 2, 3, 4, 5, 6, 7, all the way up through 20, then we can actually think of a handshake as a subset with 2 elements in it. For example, if person 1 shakes hands with person 2, that would be considered a handshake, and we'd count that as 1. Notice I wouldn't write another subset, or I wouldn't write another combination of 2, 1. 1, 2, and 2, 1 are going to be considered the same here, because if person 1 shakes hands with person 2, then simultaneously person 2 is shaking hands with person 1. That's all the same handshake. We only want to count that once. Similarly, 2, 3 is a handshake, and I could list all of these, but that's overboard. We want a better way than just systematically listing. So to think of this in terms of a combinations problem, I have 20 people to choose from, and I'm looking for all the different ways that I can pair them up in sets of 2 to shake hands. In other words, what we're looking for is 20 choose 2. How many different ways can I select 2 people without replacement and not considering the order of selection from 20 people at this party? This is 20 factorial over 2 factorial times 20 minus 2 factorial, or 20 factorial over 2 factorial times 18 factorial, or 20 times 19 over 2 times 1. Do the rest of the cancellation. Cancel the 2 with this 20 to give me 10. That's 10 times 19, or 190. That's going to take some time. 190 different handshakes, but that's the answer. Okay, that's going to wrap up 10.3.